polymorphism and polymorphism restrictions. So polymorphism we start, and it's basically when we can run functions in different ways. So it's generic functions are polymorphic. So a prime example would be length and the definitions of length, where length is a list to a integer. So this is very nice, and it's polymorphic function. We can call this with a list of numbers, with a list of characters, so a string, with a list of booleans. So that's why polymorphism is very nice. And there is this misconception that polymorphism is like freeing, and it lets us have it's like you can make any polymorphic type and it can be simple, but there are many functions that seem like they should work but don't. For example, the function in Haskell, there's a function called id. And what id does is it maps a to a. So let's say we have a parameter x and we return a. Now, if you think about it, what can we do with our parameter? Well, if we think we can do addition, that would be wrong, because a can be a boolean. So if a can be a boolean and we have to return a boolean, so we just can't do addition. But it can also be a number. It can also be a string. So there's a huge issue here. It's a simple type, yet we can't do anything. What can we do? Is we have to return x. We have to return itself, and we can't do anything else, because we don't know if it's a boolean, a string, and it could be any type. If that makes sense. Then there is this function called this function I don't think exists in the prelude, but we will call it a to b. And the reason why it doesn't exist, I'm pretty sure, let me just double check. Yeah, it doesn't exist because you'll see why it just doesn't work out for us. And that undefined that I wrote is actually a hint to why it doesn't work. So a to b takes in a parameter that's generic and must return a different type, or a possible different type, right? Another generic. So, for example, if I give it a boolean, well, not possible, it has to be a different type. If I give it a boolean, I must return something that is not a boolean. Okay, that's easy enough. But what if I give it a string? I must return something that is not a string. So what do I do with that case? I can't say true, because then what if this is a boolean? I can't say a string, because this might be a string. So what do I have to do? We have to use this function called undefined. And undefined is a function that basically emulates the type required. So undefined actually doesn't do anything useful. Most of the time it's used to like compile source code. Like if I'm writing a function like main and I don't have it yet implemented, what I'm gonna do is I'm just gonna say undefined and it'll compile. And what undefined does is whatever it needs to, whatever type main requires, it'll just emulate it. So now undefined is of type IO. Here undefined is of type B. So that's a function. Then we have a function called const. And const, before I go, this actually applies to any possibility of these types. So here equals here, this is exactly what undefined is. It basically has the same type signature. And then if I do A to B, A, B, then C, and I'll put double prime, just so we know it's a different function. And I say X, Y. So I have to make it not of type X and not of type Y. So it's the same problem. We really can't do anything. So we're going to undefine. We're going to call it undefined, which will map it to C. And so any possibility will fail. I managed to accidentally run the source code. Yeah, I wonder how I ran that. Okay, so we have this. Actually, I think it says here run code source code block execute key sequence. I think this one. No, never mind. Doesn't matter. So that's the first restriction. Then we have another restriction, and it's called const, which takes in a first parameter and the second parameter and returns the first parameter. It basically works like ID in the sense that we have a parameter which we aren't able to do anything to because that might create a type error. Therefore, if I have a const, then I must return X back, where this underscore is ignoring the argument. Okay. Now we have another function, which is the opposite of, well, not the opposite of const. It's called seek in the prelude, where it does basically the same thing, except instead of returning A, it returns B. So we ignore the first argument and say Y. So same reason. Okay. Then we have another function. This function is called that was seek, and then we need a function in the prelude. It's called has type of, which takes in two parameters of the same type and returns that parameter. So has type of would be defined as I mean, doesn't matter. We can ignore the first argument, or we can do, we can do There are two ways of defining this function. They have the same type, but they can be different. But I think has type of works like this in the prelude. It is the first function. And we can actually check has type of not in the prelude. Let me check. I thought it was has type of Haskell. Let me Google it. It does not exist in the prelude. It was only in it's only the theoretical thing, I guess. That's odd, but okay. Then we have two more functions called uncurry and curry. And remember, all of these are restricted. They can't do anything else. This is all they can possibly do with such a type signature. So we have a function called uncurry, which is a higher order function. And that higher order function takes in a tuple and executes the function on the tuple and gives an output back. So its definition is uncurry a function of xy, where f is xy. And if we look carefully, if we try to do anything with x, like add 1, add 5, concatenate, or maybe make true, we know we can't, because there is no like it's so generic that it has to work with any type. Therefore, there is literally nothing we can do with this parameter or that parameter, and all we can really do is call the function on the tuple with such a type signature. Then we have its opposite called curry. And curry takes in a tuple and calls the function on the tuple. See, and then we do curry f xy equals f xy. Same thing. We can't do anything with x, or else it might change its type or give a type error back. Same with y. Therefore, we can only really call the function on the parameters given. We're only going to be able to use what's given to us. And then lastly, for the simple ones without lists, because there are polymorphic lists as well, which I will get to, would be a function which takes in two parameters and gives an output where the two parameters are switched. So it's very self-explanatory. It calls a function where it flips the two parameters that it's received. So this can be defined as well as b, a, b, which makes it a bit easier. So this is the first parameter, this is the second. And then f is going to work on the second parameter, then first, and give a result. And we're going to return the result. So those are the polymorphic types. Polymorphism isn't actually freeing, it's constraining. And it actually sometimes can give us way less possibilities than it first seems it can. For example, if I was to basically put this in a class called number and make A's and B numbers, then the function that we call, let's say, the function that we call will work on addition. Where was I? it works on addition, which means it can be a fraction, so it can be a rational number. It could be you know, an integer, and then maybe we can make it a little more generic, and we can say real number, or maybe just real. So it works on integers, fractions, real numbers. I think that's the class. But you see how if we don't constrain it to a class, it actually becomes restrictive. So now we'll go over and see how polymorphism restricts us in lists as well, which should make sense, because if it restricts in just non-lists, then it definitely should be restricting when we introduce a list. So there's this function, I'll call it f1, which has this type signature. And so it takes in a parameter value and turns it into a list. So remember how our first function ID takes the first parameter, and the only thing it can do is return its parameter back. Well, what we can do is just a tiny bit more. What we can do is we can take that parameter and we can do this. We can return x in a singular list, or we can return x in a, you know, 2 values, 3 values, 4 values, 5 values, and so on and so on. And I think what we can do is we can do x dot 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 any number of possible ways, which will make an infinite list, I believe. I don't know if this compiles, which is what I'm gonna check. So this wrong function. This might not compile. JCI test. Yeah, it doesn't. So what we'll have to do is there's actually a function in Haskell called replicate, and we can replicate it any number of times. For example, 5 times. And we can replicate x 5 times, and it'll make a list, and we can actually check the type of replicate. It takes in an integer and a generic value and returns it in the list. So if I pass in 5 to f1, I do replicate 5, it'll be 5 5 5 5 5, like so. And we can't do anything with x, because remember, addition will give us a type error if x is a boolean, which it can be. Addition will give it a type error if it's a string. Concatenation on x will only work on strings. What if we pass in booleans? So there's literally nothing we can do. It's super restrictive on us. Now, then we have a function called, it's called f2, where we map A to B. So if we pass an x, then what can we do? Well, it seems very, hard, since this is the same problem as we had before, where A to B we were giving undefined. So so what we can do is I believe we can't do anything much. Because I think the only thing we can do is give the empty list back, which the empty list can be a part of a list of bools, a list of strings, a list of characters, a list of numbers. So I think this is the only thing we can do. And if we look at it, and we call 5, we call a string, we call a list of, just a number, true. We can't do anything else. Previously, we would have done undefined if it was like so. But this square bracket is actually a part of like is a part of all of the types, because we're just putting it can basically match to a new type if we just give it an empty list, because it can be a list of this. We can concatenate this with a list of bools, a list of strings, a list of numbers, and it will be different from this later on. I hope that makes a little bit of sense. But we definitely can't do something like this, because it'll have the same type, and that would map A to A, and that's what we did here. And we can't do addition, remember? X might be a boolean, so we can't be adding a boolean with a number. It's a strictly typed language. Haskell won't allow you to do that. We can't add a string or a character to a number. It just doesn't work. We don't know what the type is. It's too generic. So the safest thing we can do is return an empty list, which will be of a different type, and it just has no use because it's just the empty list. It's very restrictive anyway. So that's polymorphism and its restrictions. But if we introduce classes and say A is a number, then what I can do is I can return true. This will be okay. There will never be an error, because this parameter can never be a boolean, and so I can be safe and assume that that's a boolean. So hopefully that makes sense.